Good morning. Welcome to the first session of the two webinars. This first webinar will help you get started using Mathematica. This will be a 2-hour webinar with a break in the middle, so you can go and do make coffee or tea or have a comfort break. I hope you're all sitting comfortably and have a nice warm cup of English Yorkshire tea outside and have Mathematica installed on your computer. Then you should be able to follow Mark as he's going through the presentation, because you were sent a link with the notebook. If you don't have the Mathematica installed, then please talk to your administrator, because the second webinar held in a few weeks' time is really focused on your math area, statistics and all the other areas you're interested in, and it'd be very useful for you and us if you could be able to type in and do some calculations, and that will help you with your questions as well. We have a question and answer panel to the right side of your screen. We will try our best to answer all your questions, but with so many people on this webinar, it may be difficult at times to be able to keep up with your questions today, but we will try our best to try and keep up and answer all the questions that you ask during this session. Before passing to Mark, we will show a poll on your screen. Just a few questions. Please answer the questions, and then when the poll has been on the screen for a few seconds, then we'll pass the session on to Mark and we can start the training.
Okay, good day everybody. My name is Mark Braithwaite. You'll notice there is a poll on screen at the moment. If you can please fill that in, it gives me a bit of feedback on what kind of audience I currently have at hand. That way I can be more careful to answer certain questions if I know that we may need some more assistance in understanding. And that's fine, it's what I'm here for today. As you all should know, we are going to have a nice long 2-hour session. There will be a break in between, as my colleague Tim has already said, but the first part is going to be the very basics of the Wolfram language and using notebooks. And as a result, you will see me doing things live on screen. So I will highlight, I won't necessarily be sticking perfectly to the notebooks you have been given for the first 5 minutes, because I'm going to do a live demonstration, you could say. So we have the results of the poll. Let's take a look. And we have a nice little spread today, which is good to see. We have some people who have never actually touched the Wolfram language or programming of any kind. We have some people which have a bit more of a general use of programming, which is really nice. And then we have some actual programmers and developers in the audience, which is really nice to see. So we've got a bit of a cover of everybody. So hopefully we get some really nice colorful questions going on there. So without further ado, I had best get started. There we go. You should now see on your screen an image of my notebook. Cool. Just to make sure, I'm going to put my name in there. There we go. Perfect. So, as I said, we're going to start with the very basics. So before we actually jump in and start programming straight away, I'm just going to go through some of the things that notebooks in the Wolfram language are capable of. In which case, the first one we tend to like the most is our Wolfram Alpha system. I'm hoping you guys are all at least aware of the name. It's a brilliant piece of software capability that allows us to do natural language queries and have the system return results. You'll all be aware of the large amount of search engines out there where you put in some kind of text and it gives you a list of possible web pages. In this case, we've gone that step further and we want to make sure that you guys actually get an answer. So if I wanted to have a bit of fun while I'm away from the office and find out what the weather in Oxford is, which is where our office is based, so I can have a bit of fun at my colleagues, then I can ask Wolfram Alpha and you can see that it will interpret for me that question. The really clever bit here is the fact that it's already assumed certain things, like Oxford in the UK. Not only that, it's assumed that when I ask for weather, I'm looking for things such as temperature, condition, and wind speed, which I am. I essentially want to know if they had to put up with the rain. Sadly not. They seem to have some pretty good conditions if it's just cloudy. Oh well, guess they're having a particularly nice day in that case. You'll notice that it does provide further detailed information if I so choose. I'm not going to go through all the details here because it's up to you if you're interested in weather. So what I'm going to quickly do is hide that information for now. But you'll notice that I have two other possible suggestions of things to try. The second one is something maths related, because I know you guys like maths, or at least are learning maths. That's what I've been told anyway. So I'm going to try doing an integral, which I'm aware would take me a while on paper. I should know I've tried it. It took me longer than I'd like to admit. But as you can see, in a few seconds, it has already provided me the indefinite integral with respect to x that I've asked for, and a nice simple plot of that particular integral, both the real and the imaginary parts. So I'm pretty happy with that. And as I said, as usual, we have further information, including something a bit more interactive that you can play around with and set the minimum and maximum points. Could be particularly useful for some people. What I'd like to highlight is this Wolfram Alpha system has a lot of information built into it. It's essentially what it is. It's a large, massive database of information, which we've curated in such a way that we can compute answers from it. In which case, if I just want to ask what a pine tree is, I can do. Not very exciting, I will admit, but you'll find that the system understands A, what a pine tree is, and B, where it could be found. So it's pointing out that a pine tree is indeed a plant. I've got an image to kind of let me know what it is in case I'm not sure, and some information on possible growth locations and requirements. So we're not just limited to maths and the weather, we do have other information as well. For example, if you ask it what the answer to the ultimate question of life, the universe, and everything is, it does indeed come up with 42, just for those of you who are interested. So it does have cultural references in there as well as scientific data. Unfortunately, my screen seems to have paused for a second. Just taking a look. I think it's because I'm trying to load a lot of data onto my screen at once, and it's not too happy with that. So bear with me. While that's loading in the background, I mentioned that we have all sorts of different types of data available. If you want to take a look at the structure of the human foot, the skeleton of it, you can do. If you have any particular interest, you can go far as taking a look at nerves and blood vessels and all sorts of interestingly characterful stuff. There we go, and we're back. The key part of this functionality that is related to what we're doing today is the fact that you can do this kind of thing from within a notebook. That's what I'm using here at the moment. I'm using a notebook as a presentation tool, in which case I can use some of the functionality from that Wolfram Alpha system, which is the key bit is the interpreter, and allow me to do a semantic interpretation of the word sun, because the word sun could mean one of several things, which is really helpful for us to be able to get a list of them. So for example, we have the sun, which is our star. We also have this Sunday, which is an interesting interpretation as well. We have just the word itself and the family name. So it is pretty good at trying to provide us a list of possible options for our wording. And this is done in two parts. We have the very basic part, which is just linked associations of words and how they can relate to each other. And then we have the machine learning part. But sadly, we don't go on to machine learning today. This can then be plugged directly into existing data sets. So if we take a look at this simple text data I have here, it's interesting and can be considered useful, but it's even better when we get the system to interpret all those bits of information for us automatically. So what it now is going to do is it's going to go through that data and find out that those numbers were in fact currencies. Not only that, the text was in fact names of countries. So if I wanted to, I can now take a look at all these different entities like Bulgaria, because it understands where that is, the social economic situation and things like that. It is pretty extensive information. And if I wanted to, I could do a currency exchange between dollars and pounds or euros or whatever, because it understands exchange rates and things. But the great thing is that I can now go on and use this data in a simple and easy manner. So I'm trying to show you that there is all this built-in knowledge within the Wolfram language, accessible from Wolfram Alpha. And you can do some very clever and interesting things with it, like showing the ozone density around the world. I'll highlight this is not up to date, but it is a nice little demonstration. One thing I'd like to highlight is that the Wolfram language can work with pretty much most types of data. It doesn't necessarily have to be numbers. Whilst our software has the name Mathematica, that's just because that was originally our specialization. That's what we were best at. But now we do all sorts of things like machine learning. I can quite easily create a machine learning classifier in front of you guys using a set of handwritten digits and their identifying tags. In which case you can see it's doing a bit of training. Nice little live demonstration here, and it's gone well. Then we can take a look at providing that classifier function some new information and see how well it does. As you can see, it's not done so well today. That's a bit unfortunate. Anybody could get these kind of things wrong. But the key thing is it's all about probability. But as I said, sadly, we're not going on to machine learning today. Something that I thought might be of more interest to you guys would be, for example, handling geometric regions. The idea that because the Wolfram language system can handle anything as an object, two disks, for example, are just two objects which you can essentially overlap. So if you wish to do the union between two disks, you can do. If you wish to do a difference between them, again, it's just as simple. In fact, I'll even give you a very brief look at the code. It is just one simple line. Same goes for the union. If at any point you want to make those interesting shapes into something more complex, you can do. Like, for example, you can solve a 3D equation across the surface of those disks, in which case you get this interesting 3D graphic. Again, if you want more information on this kind of mathematics, it's not covered today, but it will be in a later webinar, as mentioned by my colleague Tim. A key part of the Wolfram language is the ability to create these really cool little demonstrations and visualizations. We have some very specialized ones, such as things for Julia sets and so on. But then you have the ability to really customize these things to create some interesting 3D graphics, which you can manipulate. In fact, you can even create some interesting simple manipulates where you can try using them for demonstration purposes. For example, how the manipulation of 2-point charges affects their surrounding fields. Quite nice and interesting. You could do something a lot simpler if you wish to, like, for example, plot points on a map of California, which were the epicenters of earthquakes. So we don't just do, fancy 3D demonstrations. We can do simpler things if that's what you would prefer. Then, if you particularly want to, you can string it all together to create some very interesting interfaces. So this is something we've put together ourselves, just as a bit of a demonstration thing, of an interactive interface, the kind of thing you would normally find as a piece of software, for example. In the fact I can take a look at different put options, I can change my expiry time, and then take a look at the theta as opposed to the value. It's taking a few seconds to calculate. There we go. It's changed to theta. Perfect. So as you can see, this is an interactive little manipulate that we've created that is some kind of interface. And this can be done simply as a little program which you can provide to people, or it could be done as a notebook or CDF, which you can pass to absolutely anybody. Or you could even put it online and have it like some kind of web form. The possibilities are in theory endless. In fact, that's literally what I was meant to say next. Kind of got ahead of myself. I apologize. The technologies that allow this multiple deployment capability are as follows. First, you have our web capabilities. So you've got Wolfram Cloud, which allows you to deploy everything from interfaces to APIs, or in some simpler cases, just take a look at your notebooks without having to do installations. It means you can access them from any computer you want. But we also have our CDF technology. The idea that all those lovely complex things which you create can be quite seamlessly shared with anybody else. They don't need a Mathematica license to actually interact with whatever you've created. And you'll notice here, we have the Wolfram Demonstrations project. This is a series of CDFs which have been authored so that you can pass them to others. So that way they can interact with these things and actually check out what the system is capable of. You can create them yourselves. And the last one I'm going to show you about is the Connected Devices project. The idea that the Wolfram language can essentially be placed onto any other device which accepts programming. This can be as simple as a Raspberry Pi, or it could even be your Fitbit or other small watch-like devices, whatever you choose. With these different capabilities, you'll find that you can pretty much do whatever you want. All you need is the knowledge, which is why I'm now going to start taking a look at the very basics. So let's get started. So I'm going to actually minimize my notebook because I don't need it. What I'm now going to do is give you a bit of a demonstration on Mathematica itself. So I'm going to open a new copy of Wolfram Mathematica, in which case I have a loading screen, which is unfortunately currently off screen. There we go. And then you'll find I now have my little welcome palette, which if you're following along with me, you should see as well. Your version number hopefully will be the same, but it might be 11.3, who knows. As I said, I'm here to teach you some things, so I'm going to go through this little welcome palette and highlight some key interesting features for you. You've got the most obvious, which is the New Document button, which creates a new notebook for you to take a look at. But there are other key features which are pretty useful, I would say. The first is the recent files, which for me is pretty vital. I have a funny habit of saving files and forgetting where I've put them. As long as they were the last 4 or 5 that I used, I have them listed here. You'll also notice that there's an Open from Cloud feature because it is pretty seamless, the integration between our cloud and desktop. Then you have 3 of the most possibly important buttons that you will ever find. The first is the documentation, which I will go through in more detail later. You have the Wolfram community, which is the second place you should go to if you ever have any questions. And then you have additional resources, which again, I will go through in more detail later, but includes things such as our repositories, which are stores of either knowledge or data or functionality. You'll then find that there's other access to things such as videos and tutorials and online guides as well. So, as I mentioned, the most important thing is the New Document button, and we'll click that now. So I'm going to make this screen a bit bigger so you can kind of see what's going on. When you first open Mathematica, I would say it's quite terrifying because it is just a big white blank page. And hopefully you're all following along with me now, in which case I'd like you to just straight away type in 2 plus 2 using your keyboard. I'm going to make that quite a bit bigger so you can see me typing in. There we go. Can I make it bigger again? Hopefully that helps. So you can see I've just typed in 2 plus 2. I'm not doing anything particularly exciting so far. In order to get that to work now, I just press Shift and Enter, and it gives me the answer 4. Nothing to shout home about, but that is the first bit of coding you've ever done in the Wolfram language. Nice and simple, but also quite important. What I would then like to highlight is that all of your natural mathematics you would tend to put into a calculator or write down on a piece of paper, you can do here in the Wolfram language as well. So if I want to do 24 plus 17 divided by, I don't know, 567, I can do. It will follow the expected format. And this is all well and good, you know, I can use this as a fancy calculator. It's a pretty big and overpowered fancy calculator, but at least now, using Shift Enter, you can see we can start using the Mathematica system. In which case, this system, the Mathematica in the notebook environment, has a lot of tools which are designed to help you out as you explore the Wolfram language. The first of which you'll notice is this lovely suggestions bar. Whenever you start running things in Mathematica, the system tries to help you by predicting what you might want to do next. So it's seen that I now have a rational number and is asking, okay, well, do you want the numerical value? So I can click on that and it will then give me the code required plus the answer. And then just in case it's asking, do I want to see all the digits? In which case it's actually quite a few. So you can see how you can easily step through and do some of the very basics already. And it's only been, what, a few seconds. So what I now need to do is identify the key feature of a notebook environment that you've probably missed already. And that is the cell structure. Everything in Mathematica gets put into a cell of some form. They come in different types, and I'll explain those in a second. But the important part is that this 4 is inside one cell, my calculation here is inside another, and so on and so forth. And if you take a look at the right-hand side of your screen, you'll notice that there is these interesting brackets, for want of a better word. They show you the cell structure. So here I have the outermost bracket has inside it 2 others. In which case I can quite happily click on any of those until they're highlighted blue and press delete or backspace depending on your operating system, and it's gone. You'll find that if you highlight your code and press backspace or delete, the cell is still there, so there'll be a big white space, which is why I was bringing your attention to how to delete different cells. If you want to delete groups of them, you can click on the biggest bracket that is most relevant, and then again, remove them really easily. I know, fairly simple. So why am I telling you all about this? Because it's quite important, because all your different cells have types. The first one you use is known as an input cell and can take any form of code, whether that be just maths or complex Wolfram language functions. So what I'd like to point out is that you can click on those cell brackets, then right click, and you'll see you get this item called style. I wish it was style in terms of colors or anything like that, but sadly not. In which case, we are actually talking about different types of cells. And the most important are the input, which is where you put your code, the output, which you can't actually edit, it's just what the system gives to you as your answer. You then have things such as text and title for all your word processing style requirements. And then another one that tends to be quite useful is something called code. The idea being that no matter where when you put in code, you can format it so it looks nice. That's what I'm trying to say. I lost my train of thought there, I apologize. So I've told you about cells and the fact that the notebook contains cell structures. So what's so important and interesting about this? Well, you'll notice that I can quite happily go from top to bottom and evaluate things one at a time. What I can also do is head back to a previous bit of code, change it, and run it again, and you'll find that that is the only bit that changes. It doesn't run like a script from top to bottom, which is where we get this idea of an exploration environment. in that I can hop backwards and forwards as much as I want and change absolutely anything and just run it again. So I would hope it's obvious, but just in case you missed it, it's these input and output numbers that then tell you which order everything has been run in. And if at any point you do want to just run everything in your notebook, you can head over to the evaluation menu and click Evaluate Notebook, in which case it does evaluate from top to bottom. So far, fairly simple and straightforward. What I'm just going to do is check my content to make sure I haven't missed anything. Aha, yes, there's a cool shortcut I haven't taught you yet. What I mentioned is there are different cell styles, and right-clicking on the cell bracket and choosing a cell style is fine, but some people prefer keyboard shortcuts. In which case, I can click into any cell, type in whatever I want, such as hello world, and you'll notice that it's now text. It's not code. In which case, I can use the Alt 1, Alt 2, Alt 3, and so on to change the cell style, which makes editing notebooks that little bit easier. If you're on Mac, it's not Command, there's a funny name for it. The Mac specific key plus then the number. I can imagine one of my colleagues will correct me on that in a second as to what it's called. But either way, it allows you to make your notebooks look pretty and change the type of cell really quickly and easily. So I've shown you mathematics and some text. Nothing particularly exciting so far. So before I go on to questions, I've just got one last thing to show you, which is two tools to make coding really easy, especially if you've never done it before. And the first is the autocomplete capability or suggestions system that I can quite happily type in PL and you'll see the system is already trying to guess which function I would like. Because the Wolfram language is functional. You use very simple syntax in order to actually access the language. So even if your spelling might not be on point like mine, or you're not quite sure what you're looking for, already this code assistant is trying to help me by suggesting certain functions. So I'm going to click on plot. Well, now what do I do? Well, this is where something else comes in called templates. You might not be able to see it because it's a bit small, but I have this double down arrow now present next to the word plot. When I click it, I thankfully get, well, that was there for all of 2 seconds. I apologize. You get a list of templates, which means that you can click on any one of these and it will fill in the code for you, including all of the syntax. And I'll come on to syntax after the Q&A session. So what I'm just going to quickly do is take a look at the questions and see if there's anything that requires answering. But while I'm doing that, take a look at the templates for certain functions, and you'll find that this plot one takes a function you wish to plot, the variable you're changing its minimum and maximum value, and you can tab through those pretty quickly. So if you guys take a look at that, I will take a look at the question section and see if there's anything in particular. I indeed do have 2 questions. My first one I've been given is where does Wolfram Alpha get all its data from? And how do we know it's correct? So Wolfram Alpha itself has a curated database of knowledge, which means that it's a load of data that we've collected ourselves or have been given from public sources. And we've gone through and made sure painstakingly that all the data is valid and, where possible, up to date. So most of the data comes either from open source or from companies or individuals that have submitted data which they wish to be in our database for some reason. Some exceptions to this, well, they're not actually exceptions because they are still open source, are things such as live data feeds. Weather data, for example, comes directly as a live feed from weather stations. Financial data comes in as a delayed feed from, I'm not sure exactly the location, but comes in delayed as a live feed as well. So it's a combination of data from different locations that we set up to deliberately be accessible for computation. Let's take a look at another question. Question 2, would Wolfram Alpha show me an n-dimensional space and what it looks like? That is an interesting, slightly more complex question. In some cases, if it's a low enough set of dimensions, it will attempt to try. But if it goes beyond, I think it's 3 or 4 dimensions, I can never remember which, then it will struggle and unfortunately won't be able to. It's simply to do with visualization limitations. If at any point it does start to struggle, I would recommend taking a look at Mathematica and taking a look at visualizing that space using some of the functionality present there, which again, sadly, is not covered today. And then I have one quick one. Can you please explain how to open the window you're working in? I'm going to answer this one on an assumption that I understand the question correctly. I simply started by opening Mathematica. So when you click on the icon for Mathematica, you get that welcome screen, which I showed you quickly. I'll wait for mine to come back again. So you get the welcome screen when you first click on your icon to open Mathematica, and then you simply click New Document. That's all I've done. And then I'm just working in that blank notebook so far. Apart from when I'm using my presentation, where I've gone File Open and found a particular file of my choice. And we'll come on to how to change your notebook into a presentation later, just in case that's what is part of the question as well. Okay, so that was very clever of me. I've just completely lost that little notebook I was working on, but that's fine. So we have our notebook, which we've just been putting things like 2 + 2 or I don't know, probably square root of 9, I would hope, or some other mathematics. And what we're aiming for really is to take a look at actual coding, seeing if we can do some interestingly lovely complex things with actual code. And I've already pointed out that we have a system that would allow you to type in PL and the system will check, do you mean plot? Well, yes. In which case, I'll click on plot and give a bit of a touch the drop down to get a template. I missed the word there. And then I'll click on my chosen template. And this is the point where I want to bring you guys' attention to the very basics of the Wolfram language. If you forget everything I tell you, hopefully you can remember the next few points that I will be saying, and I will highlighting them now. The first one is something we call Camel Case, which is a very simple idea of that when you name a function, for example, plot 3D, you'll notice, or actually I'll leave it there, you'll notice that all our functions have a capital letter at the beginning of each word. That is, but they're squashed together with no spaces. That's what we call Camel Case. So if at any point you're having problems with finding the right function, make sure that your first letter needs to be a capital, in which case I can then go on and choose absolutely anything. Plot theme, for example. So that's my first point, Camel Case, which is the capital letter at the beginning of each word. My next point, so I'll just make that something interesting. There we go. That's point 1. Point 2 is square brackets. Never curly brackets or the slightly curved regular ones. It's always square brackets. And there is a reason behind this, and it's because the other two have particular uses. It's all to do with mathematics, so we'll come on to that later. So point 1, camel case. Point 2, square brackets. Point 3 is commas. Commas between arguments. In theory, if you follow those 3 points when it comes to call it your programming, your code, you'll find that you will always get it correct, or should do, with a little bit of help maybe. Because for me, my spelling's particularly bad. There are 2 other points that I need to bring your attention to. And the next one is, well, how do I use my code? And I've already shown you that one without making it too obvious, and that's Shift Enter. Not Enter, but Shift Enter. That is what allows you to run the code present in whatever cell you have highlighted or you have clicked into. And that's very important. I will highlight though, if you do get into the habit of using Shift Enter for everything, like I have, most search engines don't mind, which is pretty good. Because if you type in your favorite TV program and then Shift Enter on Google, for example, it still works. It's fine. Because I now do it for everything. Cause some interesting effects. Just going to double check something. And now I have my last and possibly the most important point. If at any time you have problems, or you're not sure what function you need, or not sure exactly how a function works, or what the syntax is that you need, the first place you should always go is the documentation. And that is found in one of 3 ways. The first one is to highlight the function of choice and press F1 on your keyboard. It may be FN F1 for some people, but it should always be F1. In which case, it will bring up a documentation window like this one. And you'll notice that it's gone to the documentation window for the function I have chosen. If you're not necessarily into using shortcuts, then you'll find that the help menu has the same ability. It says find selected function and even tells you what the shortcut is. The other option is then to click on the Wolfram documentation button, in which case you'll be sent to the front page, which is nice and colourful, but could be considered as slightly overwhelming. I'll go into the documentation in a little bit more detail later. I have some other tools to show you first before we get to that point. So those are my key 5 points. If you can remember those, 1, 2, 3, 4. Oh, what did I miss out? I've told you 5, but I've only written 4 of them down. Plot theme. So camel case, square brackets, commas between arguments, Shift Enter, and documentation. No, I just can't count. I'm sorry. There we go. So those are my key 5 points. If you forget everything else I tell you, please at least remember those 5 points because they're the key point to accessing the Wolfram language. That really should be enough to get you started. But coding is quite terrifying, I would say, when you first get started. I'm not going to mince my words there. It can be quite scary. In which case, I want to bring you to highlight to you some other tools which might be incredibly useful for you getting you started. The first one is that Wolfram Alpha capability I showed you earlier. And it's not just for getting data or being given answers to things. If you click into a blank cell and press a single equals, you'll find you get this funky orange equals. It's a white with an orange background. This is also brilliant because it allows you to ask for things that normally would require coding. So for example, if I want a plot of sine x, I can ask for that, and you'll find it gives me a plot of sine x. But more importantly, it gives me the code I would need to do it, which is this lovely bit here, which if I click on, will replace my original question. you can use this for most basic functionality in the Wolfram language. So if I want to make this even more complex, again, empty cell, click equals, and go, now I want it to be an interactive plot of sine f x. And I'm deliberately choosing this one because I know that it gives me this absolutely brilliant manipulate, which allows me to change the frequency of my particular graph. No, it's gone for the amplitude. Damn, must have put a typo in there. It's pretty sad. I'm going to go slightly off piece here because I've just seen a very interesting question of how to make an empty cell. In order to make an empty cell, you can, as you move your mouse down the screen, you'll notice it goes horizontal. If you click at the point where it's horizontal, that is now an empty cell. That's why it's just not visible. So as soon as you type now, it puts in that cell for you. So I just saw that one and I wanted to explain it because I forgot that one. Thank you very much. So my lovely tool here means I can type in what I want from my code in English, and I get the code required to perform it. So I can now, if I wanted to, correct this, because I made a mistake in what I asked for. There we go. And now I have a sine curve where I can play around with the frequency, except for it's chosen some very low values. But already, I've essentially shown you guys how to become some pretty impressive programmers with very little training. So I'm quite happy with that. We already have the suggestions bar, the code assistant, and I've shown you a very cool trick from Wolfram Alpha that allows you to do coding from English. There are a few other things I'd like to bring your attention to, including the palettes. I don't know about you, whenever I hear the word palette, I think of those lovely bits of big wood that painters used to use where they'd put all their colors on. Very similar idea, but I'm going to show you what's referred to as the classroom assistant. It's the palette to rule all. And I get this lovely little additional menu that's now appeared on my screen. So why am I bringing your attention to it? Well, first, because it allows me to do mathematics in a way which looks visually appropriate. So for example, if I ask for a square root of something, I actually get the square root sign. So I can do the third root of 64 if I wanted to. So already you can use this basic or advanced tab to get your more visually appropriate mathematics. And yes, they are visual, but they are also appropriate code. So I can fill those in, and not only does it look appropriate, but I can evaluate it and get an answer. Pretty useful. But also, these palettes contain things such as your word processing abilities. If I wanted to type in hello world, and then first I change that to a text cell using one of my shortcuts, which is Shift 7, Alt 7, sorry. Pressing the right button but saying the wrong thing. And then I can increase using the buttons on that tab or decrease the size. I can change it to, I know we'll go purple today. I can change the font, underline it, make it bold, italic, and so on and so forth, as you normally would be able to in your other choice of software. So these palettes can be particularly useful, and the reason I'm introducing these to you now is because people can custom make these so that you can add pretty much any functionality you want to them, and they can look like mini programs. So I just wanted to let you know about those. So I'm just going to quickly consult my own little document on what's next. Oh, the most important that I keep mentioning and we have still not explored. Of course, the documentation. We're pretty proud of our documentation. and for good reason, in that you can highlight a function and you can press F1 and it goes straight there. So already that's quite useful. But our documentation is very, very extensive. We have a lot of information present. So you can see, I'm going to make this bigger, that we have the well, that's too big. We have the information on the sine function. Pretty good. It says sine gives the sine of a z. Who would have guessed? But not only does it give us that bit of a description of the sine function, it tends to give us some information on how it is used. So it's already pointing out that I need to use the sine square brackets of a value, close my square brackets. We then have a details section, which is for those who are a bit more advanced. So if you really wish to, you can take a look. And that includes all the abilities for options and how the system works if the function is not so obvious. You've then got some examples, which are fairly straightforward. These are bits of code on how the function may be used. There's two really cool bits of functionality I want to point out to you here. And the first one is, this is interactive. You can play around with it. And you can change it as much as you want, which is the second cool feature, because even if I decided to break this, I'm just trying to figure out how I can, there we go. When I close it, it will refresh itself as if you never changed anything. So not only does this system give you a lot of information, but it's interactive and you can't break it, which gives you some kind of testing environment before you put it into your actual code and really break something that you would prefer not to. So yes, we have a series of bits of information here, as I said, possible uses of the function, but we then have additional information such as applications, additional scope, possible issues, and some neat examples. We also have a see also section, just in case this wasn't exactly what you were looking for, which is perfectly fine also. So if I was actually looking for the cos or tan function, they're here as well. You then have some online some online tutorials. There we go. In which case it's step-by-step setups on things you may wish to try. The guides are very similar, but they tend to be a bit more either specific or broad in a lot of cases. So for example, it's this one, there is a guide on trigonometric functions. So it'll give you a list of all the functions, what they do, and which ones you might want to try. But there are also other related links as well, including access to our different repositories, online content, and additional things like that. In some cases, it could be video tutorials or access or Wolfram U stuff, if there's anything on the Wolfram University pages for to help you with those bits, those functionality or things or topics. So if you ever have any questions about functions or their use, the first place to go to is the documentation, and it's one of the most important places to go. It's always my first port of call, even if I've been using this system for goodness knows how many years now. Okay, so my last little thing before the break is going to be some very, very basics on programming. I've already told you my first 5 points, which I'm hoping you guys remember. Sadly, there's too many of you to ask the question of what were they, because I'll get hundreds of answers all at the same time. But we already have, I'll go back through them quickly. They should be still at the top, there we go. We have camel case, capital letters at the beginning of each word, square brackets, and commas between arguments. They're the main bits of syntax you'll ever need to know. You then have Shift-Enter inside a cell to evaluate it, and always take a look at the documentation if you're ever stuck or don't know what's going on. What I would like to highlight is the Wolfram system itself is pretty big. We have over 5,000 functions. And some of them have what's known as a shorthand. If we take a look at the maths, for example, 2 plus 2, that does not follow the camel case, square brackets, commas between arguments. And that's because it's actually a short form. 2 plus 2 is the same as doing the function plus, open square bracket, 2 comma 2. those are exactly the same thing. The first one is referred to as a short form, and they are all over the place in the Wolfram language. The mathematics are the main ones. For example, divide is the forward slash. You've got times, which is star, and so on and so forth, as you would expect. They're all short forms. Some of the ones you might not be aware of or might not know how to use are some of the following. I'm just trying to think of something that's a bit more complex. These are also short forms, but they're harder to determine what they're doing. In this case, you have two options to find that out, and the first one is point number 5, documentation. Highlight whatever it is you don't quite understand, and I'm going to press F1. And it's searched for that particular set of symbols and has found that they are the short form for the function map. So now you have information on that function. That's one of the possible ways of finding out what that short form is. The other one is a brilliant function called full form, basically saying everything inside those square brackets I am now going to turn into the full form you would need in order to type that into your program to make it happen again. So I'm going to put the full form of 2 plus 2 in to prove to you that I'm correct. Oops. The full form of 2 plus 2 is 4. Is that a mistake? Well, the answer is no. The Wolfram language, because it's a functional-based system, works from the inside out, and if it ever sees anything that it knows the answer to, it will do that for you first. So if you take into account the idea that 2 plus 2 is a function, it will see 2 plus 2 and it will run it and says, well, that's 4. Therefore, the full form of 4, well, that's 4. It's just a number. You can't really do anything with that. So we have a bit of a problem. We need to stop the system from being so clever. And the way we do that is using the function hold. So what we need to do is do full form hold of 2 plus 2, make sure we close all our brackets and shift enter. In which case you'll now notice everything inside the hold is now in its full form. So you can go around practicing this on all sorts of different things, like full form hold of, we'll do 1, 2, 3, 4, 5, random set of numbers. Oh, I forgot my brackets. Thankfully the system's telling me with a bit of syntax coloring there. There we go. That is in fact a list of the numbers 1, 2, 4, 5, 6. And you can do this with most things. Absolutely anything. If you ever see a form of syntax you're not quite sure what it is, you can either use the documentation or full form hold in order to help you out with finding out what they are. Which is absolutely fine. There is a capability here I've kind of ignored. I've tried to wow you with the ability to find out what full forms are. What I actually like to point out is that I've nested 2 functions together. You can put functions inside other functions. If we take a look at doing some very basic image processing, for example, I'm just going to quickly grab a picture from the web. There we go. I can quite happily sit here and rotate that image. So I've got image rotate of an image I've dragged and dropped over from my favorite web browser or search engine, and a set how far I want to rotate it. And that's perfectly fine. It will sit there and it rotate that image. A bit big, mind, but it's done the job. So I'm just going to shrink that quickly. Okay, well, I now want to, turn that black and white. So we'll binarize. It's with an A, there we go. Binarize that image. There we go. I've now made it black and white. Nice, quick, nice and simple. And that's fine. That's a 2-step process. It's perfectly valid, nothing wrong with that. But in the ideal world, we'd want to put the answer to this one into this function here. In fact, I could just copy and paste it. Why not? I've now nested one function inside the other. And there we go, there's my correct answer. And you can do this with as many functions as you want, as long as the output of one function is a valid use or input for another. You can do the same with plotting in the sine function, as I've already shown you, without saying anything about it. It's quite nice and simple. I believe I'm going to do a double check on if there are any further questions before we go to a break. Just to make sure that everything is going according to plan. Do we have any questions so far? Let's take a look. So the first one I have is, which is the most complex problem we can solve using Mathematica and the Wolfram language? Oh, that's a very interesting question. Are we talking complex mathematical problem? In which case, I would say some of your partial differential equations are the most complex, and you can quite easily do them. If we're talking complex as just many steps, then we can do as much as we want with an image. You can do full image processing. If you want something that's particularly impressive, well, you've got machine learning. You can teach a computer to recognize different types, models and makes of cars from a distance, or traveling at fast, really high speeds. Like, you can really do some impressive stuff with that kind of thing. But really, how complex the problem is limited by more your imagination than the technology, which is why most of my demonstrations tend to be pretty simple. My imagination is limited. I have another question here. Will the program be able to solve every math problem, even the most complex ones? Okay, that one I like. We are constantly updating our mathematical capabilities. As I mentioned, we started out with maths, so obviously basic addition, subtraction, and all that kind of thing. And at the time when we started, the most interesting thing we could do was plotting. Plotting graphs on a computer turned out to be really hard when computers had just started. Now we're doing complex mathematics to do with machine learning, solving partial differential equations across 3D geometric objects, you name it. But we're always looking to improve our systems constantly. That's why our version changes so often, because we always want to add the new, coolest functionality. And most of that is still in mathematics. Because as far as we're concerned, that's quite a core feature of, well, Mathematica. So will it be able to solve every math problem? If someone's found an answer to every math problem, then we'll try putting that in for everybody to use. Will the program show a step-by-step output, not just the output, but how it was derived? You'll find that that kind of requirement is mostly suited to Wolfram Alpha. Wolfram Alpha has the brilliant capability to give you an answer. So I'm just going to click into an empty cell and do my double equals to get the Wolfram Alpha question. And then I'm going to do an integral. Oh, I need something nice and complex. Integral of sine squared of, or is it sine x squared plus cos x, don't know why that's big, squared, integral of pi x. I would say that could be considered quite complex. Well, it took me a long enough time to think of something like that. So it's going to take a bit of a think. And you'll notice it's given me an indefinite integral. And you're asking for a step-by-step output. Well, I'd like to highlight that we have this lovely step-by-step solution button, which is my favorite and really did help at university. I probably shouldn't tell you that bit. But if I click on that step-by-step output, what it will now do is go through, and it's actually trying to generate a separate document for me where oh no, it's done it all here, where it's highlighted the steps that it's taken and why. In fact, you can even get a more sophisticated and full detailed answer if you want to, but I'm not going to do that because it takes more time to actually show. So just as an explanation of how I did that, click into an empty cell. 1 equals gives you the code request, and 2 equals gives you the funky orange star that allows you to access Wolfram Alpha directly from within the Mathematica. Just before we go to a break, I have my favorite question, which is, can you please tell us how you took that picture? So I am actually going to demonstrate this one. Just trying to avoid putting my web browser on screen, but we'll go with it. So I have a new tab here. All I'm going to do is go on Google, as you can see. Let me make this bigger. And I'm going to type in something I like to watch. Doctor Who. My colleagues will be laughing at me already, and I can't blame them. I'll then click on Images and just drag and drop. Honestly, you can't get it any easier than that. Just drag and drop. And already I now have a picture which I can use directly in the language for computations. Okay, so my time for this first section has unfortunately run out. What we're going to do is take a short break. Welcome back, ladies and gentlemen. We have had our 5-minute break. I hope you've had a chance to retrieve your nice breakfast, English breakfast tea, as Tim was suggesting, or taking a breast break as required. Or if you're hungry, getting some food. Probably should have done that one. Anyway, we'll continue with our little training course of going through the basics of Mathematica and the Wolfram language. So without further ado, we might as well begin. In which case, I want to start by going back to our programming. And I want to highlight that the Wolfram language, as I've said, can handle pretty much anything as an object. But there are some things that we are kind of stuck to that we need to make sure and highlight to you guys that it can do, because I'm saying it can do everything. So a bit of a bold suggestion, wouldn't you say? Well, some of the things that it can do that are quite relevant to you guys are it can handle absolutely any type of number it chooses. So you can do integers, rationals, real numbers, complexes, it doesn't really matter. But then it handles everything else as a symbol or a string. And it's using these different types that the system can do pretty much anything. For example, an image is a matrix of values. So it can handle that however it wants to. And it can be as complex or as simple as an image as you like, but the computation will still be the same. And I've already mentioned that all basic arithmetic in the Wolfram language has your expected short forms. In fact, there's one on this page I really do wish to bring your attention to, and that would be grouping. I mentioned that when you call a function of any kind, you use square brackets. Why nothing else? Well, because regular brackets has a mathematical use, if you remember, in that it changes the order of evaluation, or creates grouping, however you want to refer to it as. So if I want to do 2 of 4 times 7, that is valid mathematical expression, in which case those kind of brackets are in use for mathematics. It's one of the reasons why we use square brackets for our functions. What I would like to then bring your attention to is the 2 main building blocks of programming. And the first is assigning values to variables. And you could use the very basics and stick to things such as set. So you can say, I wish to set the symbol A to be the value 2. All done. Now, every time I use the symbol A on its own, it represents the value 2. This is quite unique compared to some other languages in that I've not told it what kind of data type we're storing. I could say x equals, go retrieve my image of Doctor Who. cut my image and paste. There we go. X is now that image of Doctor Who, just because I want to. The system does not mind what kind of data you store in your variables. Just make sure and be careful that you know what it is yourself. If you try doing 2 plus picture, let's try it. So let's do A plus X. It will give it a go. What it's doing, I don't know. In fact, it's got so confused, it's given me a white space. But at least it's giving it a try. So do be careful. That is a possible problem. The same thing, and something I would say is much easier, is just saying something equals something. Easier than writing out set every time. So if I want B to now be a particular plot of a sine curve, I can do. In which case, if I now use B at any point, you'll see that it is in fact the entire plot that I've asked for. Pretty simple and easy to go and straightforward. What you'll notice is I have this habit of putting a semicolon at the end of my code sentences. And the reason for this is it suppresses the output. If I take away this one here, you'll see that I get the image again. But I know what I'm putting in X, I don't need to see it again. So I simply go to the end of it and put in my semicolon, and it will store it without showing me the answer. If I've stored that in a variable, I can retrieve it using the variable name at any point, or I can use % to get the last thing I stored, which in this case I'm hoping is the image. There we go. But it is the last thing I evaluated, so just be careful with that one. If at any point I want to find out what I have stored in a particular variable without just doing X and giving it a go, then instead I can use question mark, which is known as information, in which case it will now tell me all the information it has on that variable. So for example, it's global, so it's accessible to all my coding, and X is currently that picture. This can also be useful when it comes to programming. For example, I can do question mark plot, and it will tell me a little bit of information about plot without having to go to the documentation. Quicker, but not as much information, so not as detailed. Still useful. If I then want to stop X being my picture of Doctor Who, because you're probably fed up of seeing that by now, then I can use the function clear and say, look, clear the variable X. You'll notice it now goes back to being blue. If I do question mark X, it's all clear, all good. In which case, we now come on to the idea that not all assignments are going to be A equals 2 and of that kind of setup. In some cases, we're going to want the answer to change. If we take a look at the function random real, which is a function that takes no arguments, because all it does is produce a random real number every time you evaluate it. So let's go again. There we go. So that has a particular use. In which case, if I was to sit here and say, well, rand equals random real, I've now stored a single random real inside that variable. But if I sit here and repeat that variable 20 times, you'll notice the number stays exactly the same. What if we want that number to change? In which case, we're going to want to use something referred to as set delayed, which is colon equals. So I'm now going to set rand1 to be set delayed random real. What this does is say every time you see the variable name on the left-hand side, evaluate the code you find on the right-hand side. Again, every single time. So I'm now going to store that. And I'm going to then call rand1 20 times. And you'll notice that the number changes to be 20 different random real numbers. And it's this set delayed ability which is actually quite important, especially when it comes to defining your own functions. The Wolfram language is brilliant and has over 5,000 different functions to it. But it won't always do exactly what you want. Sometimes you have to combine those functions together. So for example, I'm creating a demonstration function here, which takes two variables, x and y, and it will square x and add the cos of y. And the key point here is this set delayed that I've shown you previous. Another key thing to remember is to show you is that the x has an underscore after it to say I'm looking for an item and I'm going to call it x. The other one being I'm looking for a second item and I'm going to call it y, and this is what I want to do with it. In which case I can now use that function and it will give me answers. That's perfectly fine. Here's my function used, generated with several random integers. It's quite happy to use it just as it would any other Wolfram language function, and it behaves the same. In fact, if I do question mark demo function, you'll find it gives me some information about it, including the definition I wrote. Then I want to get rid of it because it's boring, so I'm going to clear it. There you have it. The key parts about defining your own function are label all the inputs you need uniquely, then specify how each one wishes to be used. Nice and simple. Also, all well so far. And don't forget your set delayed. One thing I'd like to highlight here, because I've been, pushing at you the idea camel case all the time. When it comes to labeling your own function, you can label it anything you want. So if I want to call it the function used today, I can't even spell imaginative, what a great name this is, I can do. And you're now going to wonder, well, what's the point of that? Well, when you label your functions, you probably should say what they do. But I can now evaluate this and store that. And if you remember the code, the code assistant, where you can type in or start typing the name of a function, it will fill it in for you. This works for things you've defined yourself. So if I start typing the word the, I can auto-complete it for me, which I think is absolutely brilliant. Pretty useful, I would say. Another thing to mention about the Wolfram language capabilities would be options. Options don't change how functions work, they just change the output. In which case, we'll take a look at the plot function I was using earlier. We just simply specify the variable I want to plot and the range I want to plot it over. And now I'm saying I want my resulting image to be pretty big. There we go. So it's option, this funky arrow, and then what you want it to go to. So if I want this to be particularly bit small, I can say image size goes to small, and it still plots, but in this case, the output is much smaller. How do we get this little arrow, just in case you're wondering, is you use minus and then greater than. And then as soon as I do anything else, it changes it to that nice little arrow for you. If you're using the template system, that will actually be put in for you as soon as you type in the name of a option. So before we continue, I want to bring your attention to possibly the most important other use of brackets, in this case curly brackets, and they are lists. I showed you them one example of this earlier, and they are used to denote data structures of any kind whatsoever. So vectors can be created using lists. So you've got A, B, C, 2, 3, 4. And yes, you can just add those two together because it follows the. I didn't clear A and B. Serves me right. clear A, clear B, and now we can do that more appropriately. There we go. They can be used to denote regions. So for example, here I'm saying I have a variable x and I want it to go from -2 pi to 2 pi, in which case that's now used for my plot. Iterators are the same. I have a variable I, it starts at 1, it goes to 10 in steps of 0.1. Nice and easy. So those curly braces or curly brackets, depending on what you prefer, are used to denote data structures of absolutely any kind. And as such, you can apply set theory and various bits of mathematics to them quite easily. So if we can store data sets in lists, we then need to find out how to retrieve that data. And I will tell you one thing, I don't always want the whole list of data. That'd be pretty annoying to have to deal with, especially when it's hundreds of thousands of different bits of data. I don't want to pick all of them out all at the same time every time I want to do something. And that's where part comes in. And part is the ability to, well, pick a part of a list or pick a part of a data structure. And all you have to specify is which bit do you want. So first I'm going to create myself a vector of the numbers 1 to 28 in steps of 3. There we go. And then I'm going to say, well, okay, I want part 1 of that. Nice and easy. I want part, we'll go 6 of that. That gives us the number 16, and so on. Where this is unique from other languages is that we can start at the end. So I can ask for the second from last number, or the last one before last, however you want to refer to it. I can go -6 if I wanted to, and it would give me 13. So you don't necessarily need to know how long your data structure is. You can ask for the last 4 if you wish to. In which case, you can also put in a list of numbers that you want, which parts. So for example, I'm just going to show you what range does. It gives you the numbers 1 to 5 in this case. So I can say that I want the first 5 items by putting into part a list of 1 to 5. And it would give me all those different 5 parts. Another alternative data structure, and possibly the most powerful and amazing one I've found so far, is associations. These are done on a key value pair system, in that you provide a unique key and you give it a value of any kind. In which case I have a person here called Jason, who's 24, and he has a social security number. Nice and simple is I can ask for the part 2, which this is a short form, if you remember those from earlier. What was part 2 of that association? Well, that's the name Jason. What makes it unique is that you can ask for the details by asking for the key. So if I want his name, it will then tell me it's Jason. And the reason why this is unique and different from the one we just showed on the previous page is that if these were in a completely different order, so I can put that there instead, if I now ask for part 2, that's completely different, which would be a big problem if we were using it programmatically. However, if I ask for his name, it still doesn't matter where it is, because it's still going to give me his name. So you can have sets of data which are in completely different, where each record is in a different order, and the system will not care. If something is missing, like for example the student ID of that person, it will tell you, say, sorry, missing, key absent, which the Wolfram language knows how to handle. Another clever capability is that you can nest these associations together. In which case, I'll show this bit towards the bottom of the screen, there we go. You'll notice that this faculty is a person with a name and a social security number. But they also have something called HR info, which itself is an association, which means that you can then query it saying, okay, well, I want from HR info that person's salary. In which case, there we go, 12 bars of gold. Wonder if that's quite a lot to be paid. Maybe I should ask to be paid in bars of gold. I don't know. Just a silly thing to wonder. But by allowing you to nest these things together, you can have data structures which are no longer symmetric and do not mind if one record has just a person's name, but the next record has their entire life story. And the data you can store in these can be absolutely anything. For example, we could have name, social security number, passport picture, if we wanted to, or voice clip of hello. I don't know, whatever you fancy. So it does have some very interesting capabilities. And lastly, because I've been mentioning data, just want to show you import before I take a look at the questions. In which case, import's quite nice and simple. We have a lot of different formats we support. Really cool, I think. Pretty helpful. How many are there? 211 different data types or file types we can access just by using import. Quite a lot. But the key point is how to use it. Well, you simply say import and then provide a location for your particular file. So import of, I don't know, www.google.com maybe. Let's import that web page. Oh, it doesn't like that. So if you do, because this was a question earlier, kind of trying to be helpful here, if at any point you put things into a function that it doesn't like or can't use, it will tell you. See, it's saying file www.google.com not found. Fair enough, which is why I now need to know that I need to put HTTP, and it recognizes that as a website. It will now go retrieve some information from that web page. Not very useful in this case, but it's still done it. So import can be used to retrieve files from your computer, information from the web, or even data from a database if you prefer. There's a bit of information there on relative file paths, but we're not going to go into that. Because the next thing is that we want to export our data. And this is quite fun. We don't support as many export formats, sadly. In fact, we only support 178. It's not always possible to export everything in the way it came in. But what I like is the fact that export, you tell it what you want your file to be called and what you want to put in it. Fairly simple and straightforward. So I've just saved this. Actually, I'll change it to Mark is silly. And that's me, by the way. No, I'll put I am silly, just in case. I am silly. There we go. So you know I've done it right now. In which case, I'll ask the system to open that file. And where on earth does it put it? There we go. I am silly. So you can export text files really easily. All you have to do is make sure that you specify .txt, which is one of the fun things I get to show next. If I change that to a picture format, it will still do it. No complaints, no problems. Don't know about you, but that's a lot of text. I don't think a bit of text, I don't think you can actually export that as a picture, but you can do. In which case, I've now got a very, very tiny little bit of text saying, I am silly. So just be careful when you specify your format for your export. So what I'm going to do is I'm going to take a break for a second or two while I just take a look through our questions panel again, in case there's been any further ones I've not managed to answer. If I make a mistake during input, does the program automatically identify the error? Amusingly, I've already answered that question, so I do apologize. Or that's possibly a good thing, in that if you do make any mistakes, the system will actually tell you. It will say, it will give you an error, which is designed to try help you identify what you did wrong. So I'm hoping that would prove particularly useful for you. if you then have any further issues, it's recommended to take a look at the documentation, because sometimes that can give you more information than what the error will do. Entirely depends on what you're trying to do. Have there been any further questions so far? Not that I can see, but we never know. Okay, so just a quick reminder, if at any point you do have any questions, please let me know. I'll do my best in trying to get to those during this session. If not, there will be follow-up afterwards where we will try to answer any questions we have missed. We'll highlight, there is a lot of content to be covered today. I'm not sure I will get through it all, but nothing to worry, because you will have been sent, and will be sent again, links to all the files so that you can read through them yourself. For the eagle-eyed of you, you'll notice that I had my first section there before the break wasn't done in the order in the notebook, and I apologize, but it was all present there, so you can read it in your own time if you wish to. So, a bit more learning, I would say, in which case I want to go on to programming. I'm sorry that it's a bit programming heavy, but if you want to do anything like visualizations and things like that, there are other courses, including tutorials and courses for machine learning and all sorts of other things. I can imagine my colleagues will send you information on that. But we'll continue with programming for now, in which case I want to bring your attention to the different types of programming paradigm you can do in the Wolfram language. And the first one is procedural programming. The idea that you ask a question essentially and you get a true or false result. For those of you who are already used to this kind of programming, you have this lovely table here which shows you the various different functions you'll be looking for, and or not, and so on, and what their syntax is. For those of you who are not used to procedural programming, you'll find that you can check things like, is 2 squared the same mathematically as 4? In which case, I would hope we're all aware that that should be true. But you can nest these things, you can put these things together, not nest them, sorry, in a way that then allows you to do things like, is 3 cubed 27 and 2 greater than pi? And hopefully we all know that's going to go for false, because 2 is not greater than pi. But it's these kind of abilities to check is something true or false that allows you to program in some interesting logic into your programs. And it's all based on the idea of the if statement, which is very simple, of if, then, else. So if 3 is greater than 0, tell me it's positive. If not, tell me it's negative. Well, 3 is greater than 0, thus it is positive. So I can now change this to anything else. -2, no, sorry, that's now negative. And you can use this if statement as a bit of a switch to say, well, if this is true, do this. If not, do something else. But if also has a very interesting capability in the fact that you don't need that third argument. You can just specify something to happen if you find your result is true. One possible use for this, for example, could be finding prime numbers. Here is a number, 104,729. If it's a prime number, tell me. If not, give me the next prime number. What do we get? Well, we get the number back again, because it is indeed prime. Here we have an example of what happens when it's not a prime number. It's found me the next prime number, which is 104,743. Pretty good. So you can use this to just sit there and hunt for prime numbers if you particularly want to, but after a certain point you'll find your computer struggles, so I wouldn't recommend it. Other bits of procedural programming include loops, the ability to do things multiple times, in which case you can have your do, for, and while loops, as you would expect in most other programming languages. For example, you can sit here and say, well, print I for I up to the value 5. I'll just go through and print 1 to 5. Nice and simple so far. What you could do though is you could use the different structures to multiply together 100 random real numbers between -1 and 1. In which case I'm doing the same thing with the 3 different loops. Do, what am I doing, what for? For loop, for product equals, initialize product2 to be 1, start n as 1, and while, n has to be less than or equal to the length of the list. As long as that returns true, increase number of n and multiply the product2 by whatever the next number in the list is. While this remains true, this is what you do. Just as you would expect in other programming languages. One thing that is actually quite important in programming when you get to the more advanced things is localizing your variables. And this is simply because if you're like me and tend to like using the variable x all the time, you don't want x when it's a picture to suddenly be put into somewhere where it's a number. So one of the ways of handling this is localization. To demonstrate this, I'm going to create a list of 100 random real numbers. I'm then going to set product to be 0, because if you times anything by 0, you get 0. What I'm then going to do is use a module to isolate the value of product and set it to be 1 until the module finishes. That's what it does. It says, here is a list of things that I'm setting just until the module ends, and here's what I'm doing. In which case, you'll notice I get a number that is not 0, because product has been overridden and is now 1 until that calculation finishes. Block works pretty much the same way. I get the same answer. So why is there more than one version of doing the same thing? Why have block when there's also module? The reason for this is because they do their localization in different ways. So if we take a look and set x equals to 5, and we then use module to print the expansion of 1 plus x squared. Wait. You'll notice that the x is missing. Well, kind of. You've got an x here, but it then also has a unique ID, so that the computer knows that it's a very special x that is only used in that particular instance. And that's all well and good when you're doing calculations inside the module and you don't need information from outside. But in this case, we kind of need the symbol of x to stay the same because we're doing mathematics, in which case we want to use block. You notice doing the same thing with a block gives me 1 plus 2x plus x squared. Much better. So why the difference? Well, it's because module temporarily stops your list of symbols and variables. So if you imagine x, the variable x as a box with the number x on it, the letter x on it. If we were to use a module, you'd go take that box and put it somewhere else safe for now, and you then make a new box with x on it, but you give it a unique number so you could tell the difference. Then until you're finished your current job, you use the x with the unique number. That's what module's doing. It takes all the stuff you've defined outside the module, puts it somewhere temporarily safe, creates them all over again, the ones that you've defined inside your set of brackets, and says, I'm going to use these just for now. Then when it's done, it gets rid of the temporary ones because it doesn't need them anymore. Block, on the other hand, says, you know what? X exists. There's no point me making another box for X and labeling X again. What I can do is I can take the contents out and go put them somewhere safe temporarily, use my box for my job, and then put the contents of X back when I'm finished. So it's still just X. So if at any point you use module and find that it's giving you $X $8 whatever, then you're probably going to want to use block for what you're using. So why use module? Well, module's faster. Not by much, but it is faster. So if you're doing particularly big and complex calculations, normally you want to take a look at module. But if in cases where you specifically need the values x and y to be present, then you want to use block. This then brings us on to functional programming, because procedural programming is perfectly fine and works, well, perfectly fine. There's nothing wrong with it. But functional programming does give us some additional benefits. By us as Wolfram going through and creating our functions ourselves, we can put in a lot of optimization to make things as fast and as easy to use as possible. Whereas procedural programming, you have to sit there and do it all yourself manually. So if you take, for example, the function range, what I can now do is use range to essentially create a loop which will produce the values from 0 to pi in steps of 0.1 pi. That is much faster than having to sit there and create the do loop that would do the same thing. Table is another iterative function which is much faster than having to create the do loop, or for loop or while loop, depending on what you prefer. And the reason is because we can go in with each of these functions and really optimize them as much as possible. So they're always faster than the manual equivalent. You will find in some cases you will still need to use the procedural programming, and you can't avoid it in some cases. But if you can, I would suggest using the functional versions because they're much faster. In which case, I want to bring your attention to certain functions which are very useful. And the first one is map, which is something we use at Wolfram all the time without thinking about it. And what it simply says is map this function across this set of data. So here apply the function f to a, b, and c. In which case you'll notice I now get f of a, f of b, and f of c. This ability also has a level specification where you can choose just how far down your data structure the map function applies. Here, for example, I have the numbers 1, 2, then a list, 3, 4, a list of 2 lists, 5, and then 6. And what I can now do is choose exactly where in that data structure the function applies to. So I'm going to say apply function down to level 3. And it's gone all the way into each individual element, applied function to them, then stepped back and done it again, stepped back and done it all over again. What I really wanted was it to just apply function to C, D, E, and F. In which case, I probably should specify it this way, a list of just the value 3. That's better. It now only applies to C, D, E, and F because they're the ones at level 3. Map can be used on other things, not just lists. It can be used on other data structures, but it can also be used on other expressions. In which case, I can take A, B, C, D, and E, and I can apply function to each of them before adding them together. Nice and simple. And I've previously mentioned the short form for map, which is that /@ again. So fun mapped to this information does the same thing again. Okay. So before I take another look at the question section again, we have thread and apply. In which case, thread is like sewing. You're trying to you're trying to connect 2 different bits of data together using a function. So for example, here I'm applying f to a and 1, then b and 2, c and 3, and threading them together using f. And this can be done with options. So I can thread these 3 bits of data to these 3, Doesn't necessarily need to have that function defined at the beginning, but you can also just use them to combine two different sets of data into pairs. What I'd like to highlight is that thread is a mathematical matrix function, which means that everything either has to be the same length of 3 in this case, or of a single element. In which case I can thread those 3 things together with double A in the middle of each triplet. So I'm just going to quickly take a look at the questions panel and see if there is any further questions so far. It looks like my colleagues are ahead of me. Ooh, I just gained a question. Can I give different variables values from outside, or should I declare everything from inside? You're able to pass variables in and out of a module or block, because that's what I'm assuming you're referring to. In which case, in fact, I'll go back to the module and block just to, so I don't have to recreate examples. So I'm just going to grab this for a second. What would be really good would be a blank page. There we go. I'll go back to my test notebook from earlier. So we have our module, nice and big so you can read it. And it currently has green values, which are from inside, which you'll notice are specified inside the module, but list itself was specified outside the module. So they are automatically handled, and it will find the items that are outside. It's only the items which are listed here which are defined inside and are therefore kept inside until the module is finished. So if I wanted to now name list equals 1, 2, 3, 4, you'll see that list now goes black, and it's quite happy to find that from outside. So it is a suggestion that if you already have a variable that exists and you want to replace its value for the duration of the module, then label it here. If you've got bits of data that you're only using for, in this case, this particular calculation, then again, define it here. That way, when you're finished, all that extra data you don't need gets thrown and cleaned away. It's better for your memory use. And also, if you're like me and tend to use the same variable multiple times, then putting that inside a module before you run your code will save you from suddenly inputting an image of Doctor Who into a plot. So yeah, modules for variable and blocks for variable localization tend to be a very good idea. So we have 5-10 minutes left, in which case I'm just going to, whoops, that is module and block. We've gone through this bit. There you go. I'm going to show you apply and 1 or 2 others, and then I will hand you over to my colleague Tim again. In which case we have the function apply, which has a short form of double at, and it replaces the head of an expression. This now highlights that I've forgotten to tell you something earlier. When it comes to all expressions, they follow the same form. If you remember, we have our camel case, which I'm just going to use for the current image for some reason. I'm not going to evaluate this. We then have arguments, sorry, square brackets with commas between arguments. The head of an expression is the title or the name of it. That's all I mean when I say head of expression. So if we take, for example, a list of numbers 1, 2, 3, 4, 5, the head of that is in fact the word list, which is why our indexing does not start at 0. So if I want to take part of that list, so list equals, if I do list part 1, that will give me the first number. And the reason being is because if you were to start this at 0, you get the head of the expression. So that's the head of an expression, is the first thing you see when you do full form of something. It could be then the word thread, the word list, and so on and so forth. And apply allows you to replace the head of that expression with something else. So here normally I'd be doing a function applied to A, B, and C, but I can replace that with function G of A, B, and C. In which case you'll see both the full form and the short form do the same thing. Easiest way to find the head of an expression is to use the function head. Who could have guessed? In which case, we get the answer list. What I can do using apply then is change this from a list to a series of multiplications quite easily, just by using apply of times. So apply does have quite a lot of different uses and is very flexible. In which case we're going to go on to a slightly more complex topic, which is anonymous functions. The key part of this is all boils down to programmers are lazy. We like to do as little effort as possible for as much return. And that's a good idea. You don't want to put in a lot of effort and not really get anything out of it. In which case we have our usual function definition here in full of here is my function. It's called f1. It takes an item which I'm going to call x and it does the following. That's your full form version of your function. Nice and simple. But really, I'm getting a bit lazy and I want to type less. So I use this. I'm going to define a function. I'm going to call it, it's going to take a variable called x and we're going to do this to it. I'm going to store it in f2. In which case you'll find that that still works as the rest of the system would as well. But again, still want to be lazier. Less typing, please. So I have a function. It's going to take an argument and it's going to put all those arguments where you see a hash. That's faster than having to type in x every time. And you'll notice I'm no longer specifying this list here. That works just the same. No problems so far. But I want to be lazier. I don't want to have to type out the word function every time. So let's use the short form for that. We open a set of brackets, type in what we want our function to do using hashes, where we want variables to be put, and then put an ampersand after we've closed our brackets. That's, I would say, is pretty lazy and pretty fast to do. But we're not quite done yet. If I'm only going to use this function once, there's no point in storing it anywhere. In which case we get this. Hash squared plus the exponential of hash minus 3. That's my function definition. And then I'm going to apply that to the number 1. In which case you'll see I still get the same answer. That one at the bottom is referred to as anonymous function. It's very simple and really quick. You open your brackets, you specify what your function to do, what you want your function to do using hashes where inputs need to go. In which case, if you've got multiple inputs, you can use hash 1 and hash 2, for example. Then you close your brackets and you put your ampersand. The ampersand says everything inside these brackets is an anonymous function, so please pay attention, Wolfram. You can then specify what arguments you want to put in there, and the system will handle that appropriately. Amusingly, that's just turned up as a question, and I'm afraid I've just answered it. So I'm glad I'm on that one. I'm glad we're thinking the same way there. So what's the point of these anonymous functions? Well, as I said, they're for when you want to be lazy, really. But it's all about using them for things such as list. In this case, I've got a list of values. And what I want to do is I want to apply a function to all of those values without having to specify or store that function elsewhere, because I'm not going to use it again. I'm going to use it for this map and that is it. So there's no point storing it, so I might as well use an anonymous function. In which case I want to check the head of those values and find out, is that the same as the head integer? In this case, I'm missing my brackets, so I'll put those in so the system knows exactly where that's going. And then I'm going to apply that to my list. And what it's going to do is give me a list of true or falses telling me whether or not those are integers. So that's my last little bit on anonymous functions. As we've only got 3 minutes left, I'm going to take another look at the questions just in case before handing you over to my colleague Tim. As I said, it's a bit sad that I haven't got through all the content today, but that's fine because you guys have access to all of it, and you'll also hopefully get a copy of the recording of what I've done today as well. So just a quick look at the questions in case there's any further ones. We have access to the tutorial. Tim's already pointed out, yes, we'll email you the links. Cool. Why do you use ampersand after the function? There we go. See, I did answer that one, so we're good. Looks like we have got all our questions answered so far. So I will say thank you very much for listening, and I will pass you over to Tim. Thank you.
Hello, Mark. Thank you very much. Hopefully everyone enjoyed. I know it was 2 hours. We had a break and some QAs in the middle, but hopefully it's a good introduction to the Wolfram language and Mathematica. The next one is going to be concentrating on areas that your specifically area of study, so discrete maths, calculus, statistics, and how to use the Wolfram language to help you in your studies throughout your course. And I think the next one is going to be, assuming that you've done this course. I think there are a few people who weren't attending this course, but you will be emailed a link to the recording with also the notebook as well, because I know some of you were unable to locate the notebook because some of you still don't have a license. That was one of the questions that was asked. So what I'm going to do is after this webinar, I'm going to send a message out to the project coordinator, just making sure that everyone is aware on how to get a license of Mathematica and install it onto their computer, laptop, or whatever you're using. Because I think the next session is going to be very important that you do have the software installed. As a backup, there's a 14-day trial, and there's a link, I think, in one of the answers to the questions that I sent to everyone. But we prefer to have you, a proper license. The trial is fully functional. It's not crippled in any way. There's no functionality removed. You can still do neural networks and linguistics and all those wonderful things. It just has a 14-day limit on it. So again, thank you to our team here in Oxford and Mark for organizing this in such a short time. Again, we have recorded it. We will send you that out, all that information to you. And I believe the more math-focused session will be on the 10th of March. I'm not sure at the exact time yet, probably around the same time, but you will receive an email with a link and everything else for you to join us. And all I can say is thank you for attending. And when you do receive an email from us, if you still have questions, then please reply to that email with any questions you have, and we will do our best to answer. Mainly Mark, really. He's the guy who knows it all, really. But we will do our best to answer your questions. And also, I sent a link on the documentation. Please explore the language. There is so much in there beyond just math, discrete maths and statistics. If you want to create your own AI chatbots, there's those things. There's all sorts of other functions for linguistics and interpreting languages and reading speeches and books and working out sentiment. And it's a huge area to explore beyond maths. Anyway, 1 minute over. Thank you very much. And I hope we'll see you all again on the 10th of March. Thank you very much.